So picking up where I left off, you need to find the slope of that third line. So M3 would equal the delta y over delta x. And again, you're looking for 2 points that are easy to read. Again, lucked out. 1, 2, 3, 4, 5, 6, 7. So it looks like a 7. And that's over a 1 second time period. So 7. So my V3 is equal to the negative reciprocal. So that would be negative 1/7 or negative, and 1 divided by 7, about 0.15, negative 0.15 meters per second. So there we are. We can then move on to our velocity time graph. So the velocity time graph, I'm going to have to adjust a little bit. So if we go up by, got to go 0.08, 0.15. So if I go up by, let's change the scale here. You can keep it simple if you want. Keep it to 0.5 and 1.0. All right. It'll be a little tighter, but still works. Okay. So my first value was 0. The next one I took at 4 seconds, and I found it to be negative 0.08, so just a little under negative 1. So you can see you're staying tight to the x-axis, but it's an approximation anyway. And the last one was negative 0.15, so that was at 8 seconds, so negative 0.15, somewhere in there. So now you draw a line of best fit, so that's the one that best goes through all 3 points. I'm not sure whether my smart board can handle that. It's too small of an angle. So I'll undo that, and I'm going to try to, I'll freehand it. Probably not the best, but all right. One of the drawbacks to the smart board. So there we go. Now we want to find the acceleration of the system then. So the acceleration then would be, again, you're always going to end up with a linear relationship. So delta y over delta x. Pick that point there. You know it's, and if you want to be as accurate as you can, you use the negative 1/13 divided by 4. And what you end up with there, so 1/13 divided by 4, you get 1/52. That would be negative 1/52, which is approximately equal to negative 0.02. So just cleaning this up and finishing it off. I'm going to have to change that scale again to negative 0.05, negative 0.01, 0.05, 0. I guess it'd be 0.1. All right. So we know that the slope was approximately 0.02, and it would be negative, so it'd be right there. So there we go. There are our stages we have successfully found. And because it's a negative acceleration, it means we are backing up. We are speeding up as we are going. So from that investigation did earlier, you're speeding up backwards. So it makes sense that your acceleration is increasing in the negative. Last example that I want to go through here is I want you to be able to go from an AT graph going the opposite direction all the way to a DT graph. So if we're going that direction, we already talked about it, it's going to be area. So you need to find the regions. So I have 1 area, 2 areas, 3, and 4. So we need to find the area of each region. So area 1, and again, it's all rectangles in this case, so it's length and width. So we are going the opposite direction. So that means we need to find area. It's the area under each segment. So here we would have 2 times 2. So it would be positive 4 meters per second this time. Now before, remember, we were finding the area from a VT graph. So we were getting meters. Now we're getting meters per second. Area 2, again, length and width. It's a rectangle. 2 times, and this time it looks like it goes down to 1, 2, 3. It looks like it's supposed to go down to 4. And it's going to be negative 8 meters per second. All right, because the area is below the x-axis, we consider it to be negative. Area 3 is really nice. It's 0 meters per second. And area 4, again, length and a width. So we end up with 2 times 1, 2, 3, 4. And it'll be a positive 4 meters per second. So here we are. From that information, you can create your velocity time graph. It'll be a series of lines. So I'm going to start it at 0 meters per second. You can technically start at any velocity you want, but in this case, I'm going to start it at 0. It just seems to be the more simple place to begin. So the first two seconds, I need to be going 4 meters per second. All right. So I'm taking these values. Those are the only ones I'm really concerned with, and they're corresponding times. Now after that, I'm going to decrease or go down 8 seconds, and that is in the next two. So here's 2 seconds. Here I'd be going 4, 5, 6, 7, 8. So now I'm going negative 8 meters per second. Or sorry, I've decreased by 8 meters per second, which means I'm going negative 4 meters per second. For the next segment, the area is 0. Also, the slope is 0. So that means I'm going to have a horizontal line here for the next 3 seconds, or 2 seconds, I should say. And finally, I need to increase 4 seconds over the next 2. So, end up going 0 meters per second. All right. You can double check, but you know 4 take away 8 plus 4 is going to give you 0. So there is my VT graph. Okay. Now, last step is to go to your position time graph. All right. So if that's the case, I'll go like this, find area. We need to take those shapes. So we need to find the area with the x-axis. So for some people, it's going to be a little bit disappointing, but we actually have 1, 2, 3 areas to find here because it's with the x-axis. Okay. And you do have to break it into right triangles. I can't find the area of this entire triangle because there's a change in that slope. Okay, whenever you have that change, you have to break it into a new shape. And then I have 4, so I have 5 shapes to find the area of. So going through this, area 1, 1/2 base times height. So that's 1/2 times 2 times 4. So we end up with 4 meters. Area 2, also a triangle, base 1/2 base times height. Base is 1, height is 4. So we end up with 2 more meters, and both of those are positive. Area 3, triangle, 1/2 base times height. 1/2, the base is 1. Height is negative 4. So we end up with negative 2 meters. Area 4 is equal to length and width. It's a rectangle. So we've got it going for 2 seconds at a height of negative 4. So that gives me a value of negative 8 meters. And finally, area 5, 1/2 base and height. 1/2, the base is 2. Height is negative 4. So we end up with just negative 4 meters. Okay? So there we are. So I'm going to translate those values, and this is where it becomes, the conversation becomes important, or listening to what I have to say. I know that's shocking, but here we go. So area 1 is going to be 4 meters. So I'm going to plug that in first. And then the next one is 2 meters further. So that goes 2 seconds and then 1 second. So this is a bit of a challenge for myself here. So here's our position time graph. We're going to do meters on this axis, time on that axis, and do I have them? Yeah, these 8 seconds. So the first one, here we go. So going back, it said that in the first 2 seconds, I got to go 4 meters. So I'm not going to do lines here. I'm just going to put dots. So 2 seconds at 4 meters. A second later, all right, so if I go back, in the next second, I have to go 2 more meters forward. So 1, 2. Going back again. In the next second, I go back 2 meters. So the next second, I go back 2 meters. So I'm back to here again. And then in stage 4, I have to go back 8 meters over the 2 seconds. So 8 meters over 2 seconds. So 2 seconds, 8 meters. So that's at positive 4, so down to negative 4. It's going to be down here. And then the last dot, so I'm just doing the adding and subtracting to start. I'm not doing the connections yet. And in the last 2 seconds here, I have to go an additional 4 meters back. So another 4 meters. So 1, 2, 3. Okay. Now, this is where that investigation comes in handy, and you need to understand what's going on in each segment. So in segment 1 here, all right, segment 1, we're getting faster, our velocity's increasing. So if you remember back when you're walking toward and away from the wall, how would that look? Well, if our velocity starts at 0 and we start moving faster, your graphing calculator, the curve had to look like that. In segment 2, you are now slowing down until your velocity is 0. Okay? Your velocity in a position time graph, velocity is 0 when the tangent's horizontal. So I'm just going to make a note here. Okay? At vertex, I'll call it a vertex, on a PT graph, velocity is 0. Okay? So that means that each segment here, I'll just trace it again. I start walking away from the wall fast, and then I slow down and stop. All right? That's what's happened here. In the next segment, I now start backing up. Okay? I start backing up, and I'm getting faster as I back up. So if I get faster as I back up, that means my curve is going to go this direction. So that's, again, it's like that investigation. What happens in the next segment? My velocity stays the same. I remain constant. I walk at a steady pace. That means that I end up with a line. So that means I need to connect those 2 points with a straight line. And finally, what happens? I now start to slow down until my velocity is 0. So that means I'm heading toward another vertex. How do I slow down if I'm walking backwards? I get a curve that looks like this and creates a new vertex. A little better job than that. So it slows down until I reach 0. So there we go. So again, if you watch your velocity graph, started at 0 and I sped up, and then I slowed down and came to a stop. So that's when the velocity graph crosses the x-axis. I start backing up faster, and then I travel at a constant speed until I start slowing down back to 0. So here's your resulting position time graph. When it's non-uniform, you'll end up with curves, and they are actually parabolic curves. So that's why I can use that word vertex. So same thing here. Velocity is equal to 0 meters per second at any vertices. Okay? Going to be the biggest challenge. The homework today, it's just a handout. So make sure you go through and you try those questions. Very important to understand it. Make sure you have the investigation out to remind you of what the position time graph looks like matching up with a particular motion. All right. If you have any questions, you want anything clarified, please make sure you track me down or ask me in class.